shows a solar photovoltaic array on a Minnesota farm. This array provides enough power to completely supply the farmhouse and generates about $300 to $500 per month income through sales of the excess power to the local utility. In this video, we will talk about how this works and explain how solar energy can be used for direct heating and for electricity generation via concentrated heating and photovoltaic cells. We will also discuss some of the trade-offs associated with large-scale solar energy production. Solar power is the fastest growing renewable energy source in the U.S. However, it's still a smaller energy source than other forms of renewable energy like wind and hydropower. Solar now contributes about 9% of the renewable energy portfolio, which means it generates about 2% of the electricity produced in the U.S. Globally, China leads the world in installed solar capacity, but the US comes in second and Japan is in third. There are several ways that we take advantage of solar power, but they all have the commonality of not emitting greenhouse gases or other forms of air pollution after manufacturing. The energy return on investment, or EORI, for solar photovoltaic technology is about 10. Which is less than oil and gas, but more than the tight oil and tar sands methods of petroleum production. Solar energy is the sun's radiation reaching the earth, and it's not evenly distributed everywhere. This map shows the annual average solar radiation in kilowatt hours per square meter per day. As you can see, more solar energy is available in tropical and subtropical regions and deserts where there is little cloud cover. Much less solar energy is available as you move toward the temperate and polar regions. By the way, this uneven distribution of solar radiation is what sets up the global patterns of ocean and atmospheric circulation. So it's important for far more than just where good places to invest in solar power are located. Let's focus in on the US, where this map shows that some parts of the continental United States get about 1.5 times more solar radiation than other parts, and Alaska gets very little. Here you can clearly see the difference between sunny deserts and more humid and cloudy areas at similar latitudes. And this map should be giving you a hint that large-scale solar energy is going to be a much bigger deal in the southwestern US than in northerly states. But the map should also suggest that small-scale solar installations, like those used to heat or power individual houses, are possible pretty much everywhere in the US, except maybe Alaska in the winter. We all know that on a spring or autumn day, it can be downright chilly in the shade, but warm and pleasant in the sun. This is because when we are out in the sun and solar radiation strikes our skin or clothes or other solid objects, the solar radiation converts into thermal or heat energy and warms us up. The same principle can be applied to heating our homes. This can be as simple as having large south-facing windows in the northern hemisphere that are shaded or blocked by deciduous trees in the summer, but in winter when the leaves are off and the shades are open, sun passes through the window, strikes objects in the room, and is converted to thermal energy, warming up the room. Other solar heating schemes add on to that principle by using mechanical systems to circulate warmed air or water. For example, the sun can be used to warm up water through a rooftop installation that is oriented to maximally capture solar radiation, like the image on the top right. Then the warmed water is used to pre-warm water for a conventional hot water heater, saving the gas or electricity that would normally go to heating up cold water. This can be a big energy savings because a conventional hot water heater can be about 15% of a homeowner's utility bill. The warm water can also be circulated through radiators, which then warm the room air. This sort of system is shown in the bottom right image. The great thing about solar heating is that once a building is designed and built this way, the energy is completely free to use. A second way that we can make use of solar energy is through concentrated heating. Using this approach, the solar radiation is focused into one area where it is captured by an absorbing material that heats up. A small-scale version of this approach is found in solar cookers, but it can be used at a much, much larger scale to generate electricity. Here's how it works. A concentrated solar plant has a field of rotating mirrors that follow the sun and reflect the light into a single place. In that receiver, there is salt, which becomes molten at 500 degrees Celsius, and the heat gets transferred to water, which becomes steam. The steam then spins a turbine attached to a generator and produces electricity. There are several different designs of these plants. The ones shown in Spain and California have mirrors that reflect light toward a central tower, while the plant in Morocco uses curved mirrors to concentrate light into the pipes supported just above the center of the mirror. The really cool thing about this form of capturing solar energy is that the salt stays hot enough, long enough, that the plants can generate energy for about 3 to 8 hours after sunset. The concentrated solar heating process is about 7 to 25% efficient, which is comparable to or better than solar photovoltaic cells, which we'll talk about next. However, photovoltaic cells are now cheaper for the same amount of energy, so concentrated solar power is less popular than it was between about 2006 and 2014. The US and Spain have the largest concentrated solar power capacities. The most common way of harnessing the sun's energy is through photovoltaic solar cells. These cells take advantage of the photovoltaic or PV effect. Solar energy creates a separation of positive and negative charges in a solid material as a result of the excitation of an electron. In other words, photovoltaic cells work by causing a physical or chemical change, as opposed to simply heating up. This photovoltaic effect works in certain materials called semiconductors, which have intermediate conducting behavior between metals, which are freely conducting, and an insulator, which are non-conducting. When sunlight strikes the semiconductor, some of the photons are absorbed, which dislodges electrons from the alloy. These electrons then start moving in a circular path between the semiconductor surface and internal layers, creating an electrical current. The most common material for photovoltaic cells is elemental silicon, but other materials can also be used. Commercial cells are 15 to 20% efficient, usually used in an array of several cells to supplement the energy in a home, or huge solar farms to generate utility-scale electrical production. The major limitations to solar photovoltaic systems are the high cost of cell production and the fact that storage is needed at night and on cloudy days to ensure an uninterrupted energy supply. Thin film solar cells are an emerging technology that is used in things like portable solar chargers, but can also see larger scale applications. The thin films reduce the amount of material required in creating the active material of solar cells, but the majority of film panels have significantly lower conversion efficiencies than traditional rigid solar photovoltaic cells. This lower efficiency means correspondingly larger areas must be covered to generate the same amount of electricity. One increasingly popular application of solar photovoltaic cells is on rooftops of homes, schools, and businesses. Rooftop solar panels can be tied to the electrical grid or create a self-sufficient off-grid building. The top image shows a small energy-efficient house that is powered entirely by the solar panels shown on its garage and shed. The bottom image shows the garage of a grid-tied house with sufficient solar panels to provide enough power on sunny summer days, but which uses energy from other sources on cloudy days and in the winter. Both houses are at the same latitude in the upper Midwest. If rooftop solar is grid-tied, the owner may be able to sell excess energy generated to the power company via net metering. When they are making less energy than they need, they draw from the electrical grid. When they make more energy than the building needs, they sell it to the electrical company and make money. This avoids the need for battery storage for many rooftop solar installations, and is how the farm I pictured at the beginning of this video is able to make several $100s per month with its solar panels. Each state sets its own rules and incentives and restrictions for rooftop solar and net metering, and some areas, like California, are now mandating solar panels for new homes. One concern about rooftop solar is the high upfront cost of installation relative to the payback from reduced electrical bills. But with net metering, tax incentives, and decreasing costs of solar photovoltaic, this may become a less significant barrier in the future. One advantage of rooftop solar is that it is a decision that individuals can make that directly affects their energy footprint, unlike things like hydropower and nuclear that are out of the reach of most homeowners. Now that we know how solar technologies work, let's turn to some of their limitations. Large-scale installations such as concentrated solar plants and solar cell farms require a lot of space. Unlike wind farms, the space in these large-scale installations cannot be used for anything other than energy generation, although there are ideas for ways to mitigate this impact, and rooftop solar doesn't require any additional space. Some of the best areas for solar power production are in sensitive desert habitats, and as sites are converted to solar installations, habitats for ground-dwelling species, like the desert tortoise, are disrupted or lost. Concentrated solar projects have also raised concerns with bird kills because insects are attracted to the reflected light and birds fly into areas of high heat in search of the insects. Some of the bird-related concerns can be mitigated by ensuring that not too many mirrors are focusing on the same pathways at once. Another limitation is water. Concentrated solar plants based on steam require a lot of water, which is usually not abundantly available in regions with abundant land and sunlight. However, there are ways to allow the steam to cool, condense, and be reused on site, which lowers the demand on water. Some water is still needed to keep the reflectors clean, however. Solar photovoltaic cells don't require much water during operation, but the manufacturing process is water intensive, just as it is for other semiconductors like computer chips. However, when considered relative to some other forms of energy production, the water use is not that high, although it is higher than wind energy. The photovoltaic cell manufacturing process also requires some hazardous chemicals to purify quartz into silicon and etch the surface to collect light. And thin film technologies are based on materials like cadmium telluride, cadmium sulfide, and copper indium gallium selenide. These elements are much less abundant than silicon, and some are toxic, with potential health consequences for miners and others along the steps of the production process. Solar panels have lifetimes of 25 to 30 years, but more options for safely disposing of and recycling the materials are needed as more solar panels reach end of life. Producing the materials for solar energy generation is also energy intensive. Considering the full life cycle of different energy sources from manufacturing to energy production to disposal, solar energy has a much lower greenhouse gas emissions footprint than fossil fuels and is better than or comparable to bioenergy sources. But solar energy does have higher greenhouse gas emissions than other forms of renewable energy. To summarize what we've learned, there are three main ways we take advantage of renewable solar energy: solar heating, concentrated heating, and photovoltaic systems. All solar energy is renewable and doesn't produce greenhouse gas emissions or air pollution, aside from the manufacturing or construction process and end of life. The energy return on investment is less than most fossil fuels and some renewables, but as the efficiency of solar photovoltaics improves, the EROI will increase as well. Full reliance on solar energy is likely to be regionally limited by solar radiation, but rooftop generation may be a widespread way to supply part of our energy needs and can be implemented by individual homeowners. And, as with every form of energy production, there are environmental trade-offs that must be considered.